So the next problem I want to look at is problem 11 from chapter 8. In this problem, they're asking us to solve for the null geodesics in the three-dimensional flat spacetime using polar coordinates. Do light rays move on straight lines? Now, I'm not going to solve this problem completely. In fact, I'm going to reduce it to the previous problem. I will obtain some equation and claim that this equation is already solved, which it is. Right? So in the three-dimensional flat spacetime, our line element is actually given in the book. This is minus dt square plus dr square plus r square d square. Now, we are looking at the null geodesics, so we are looking at photons, light rays, whatever you want to call them. Now, how would you obtain the geodesic equation for such a problem? Now, one thing you can do is you can write the geodesic equation for the photons. So remember, we had a geodesic equation that looked like this. So we don't have our proper time, but we have some affine parameter, and this is equal to beta gamma dx beta by d lambda dx gamma by d lambda. Now, you can obtain the Christoffel coefficients for this metric by using the equation for the Christoffel symbols, and then you can write down these three differential equations. It's not too hard. I actually did calculate the non-zero Christoffel coefficients, but I made a mistake, and I'm not sure where I made a mistake. I made a factor of 2 mistakes somewhere. But then you are going to obtain second-order differential equations, and they are going to be somewhat nasty to solve. Right? So another thing you can try is that you can start from the variational principle. You can write the action, and you can identify your Lagrangian, and then you can write down Euler-Lagrange equations. But there is an easier, more straightforward way. Now, this line element, and consequently our metric, contains a lot of symmetry, contains a very high degree of symmetry. Now, the metric doesn't include t or phi, so there are going to be two killing vectors that correspond to this symmetry. Right? So if we write these, I'm not going to use Greek psi for this. I'm going to use k1 and k2 as my killing vectors. So one of them is going to be something like this, corresponding to the fact that there is no t dependence in the metric, and the other one is going to be something like this, corresponding to the fact that there is no phi dependence. Now, we can't write something similar for r, though it's possible that there's another killing vector that corresponds to some kind of symmetry of this problem when it's written in another coordinate system, right? If you wrote this in Cartesian coordinates, then you would have 3 killing vectors. So there might be another killing vector that's not easy to see. But these two are going to give us 2 constants of motion. And remember how we obtain the constants of motion. We take the dot product of these killing vectors with the for velocity, not the for velocity, but the tangent vector to the world line, I should say, because we're talking about light rays, so it's not really for velocity, but the tangent vector to your world line. So this dot product k1 is a constant of motion. I'm going to call this E, because this corresponds to time translation symmetry, and that's usually associated with the conservation of energy, and E is the short note for this. And actually, this is going to be minus E, right? Because this is going to be pick up a negative sign in the dot product from the metric, so let's call this minus E. It doesn't really matter. And the dot product of this U with the second killing vector, I'm going to call this another constant of motion. I'm going to call this L, because this is some rotational symmetry, and rotational symmetry leads to conservation of angular momentum, and L is the shorthand for angular momentum. So what do these look like? So let's write the dot product for the first one. So that is going to be the t by d lambda, a minus sign, times this. This is just the first element. It's just 1, right? Is going to be minus E, and therefore dt by d lambda is some constant E. So this is my first differential equation. The second one is going to be, from the metric we have r square, then d phi by d lambda. From here we just get 1, that is going to be equal to L. So d phi by d lambda is some constant divided by r square. So that's my second differential equation. Now I have three variables. I have three coordinates, I should say, t, r, and phi. So you might be thinking, okay, now since we don't have a killing vector corresponding to r, we need to write down some differential equation like this, or starting from the variational principle and obtain a differential equation that way. But no, we do have another constant of motion, and that is the dot product of our tangent vector by itself is going to be 0. Our tangent vector for null geodesic is a null vector, and it is this. So how do we write this one? This is gonna look like minus dt by d lambda square plus the r by d lambda square plus r square coming from the metric d phi by d lambda square is 0. So I can write this as a differential equation for dr by d lambda. So dr by d lambda square is going to be, if I take this to the other side, this is going to become e squared. This is going to be minus r square L by r square square. Right, so this is e square minus L square by r square. And if I take the square root of this, I'm going to get dr by d lambda is equal to e square minus L square by r square to half power. So I have a third differential equation. Now I want to look at the shape of the geodesics. Right? What I'm interested in, how do the light rays move on straight lines? So for that, I'm going to take the ratio of these two. So right, let's call this 1, let's call this 2, divide 1 by 2 and make all the mathematicians scream in horror, and we get d phi by dr is equal to L by r square e square minus L square times r square to minus a half. Right? So this equation is very, 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 very similar to equation 8.36 in the book. Right, the only difference is here is that instead of 1 we have e square, but that's a technicality. You can take this into a common parentheses. You can write this as L times e r square 1 minus L over e square by r square to minus a half. Right? So you can see that the form of the equation is exactly the same as what you would see in equation 836. So the conclusion from that equation that this in fact describes a straight line also holds for this case. So for this metric over here, for this metric, the light rays do indeed move on straight lines.